and it looks to be about 10 acres in size. Next step you do, and I'm going to kind of skip through this quickly, but once you identify these anomalies in the seismic record, you have to model them and compare the model to the real record. And basically you do that by what we call fluid substitution. We have, one of the wells out here has a sonic log. We can create a synthetic seismic response from it, and we can inject that seismic model with gas. And when we do, we get I'm going to toggle back and forth between these two next to that yellow arrow, right there, and I get a change in this seismic response when I compare it to the actual rock record. So that's a positive thing, that I can actually model it against the seismic, and I get a good, clear seismic synthetic response. And then I can forward it and actually compare it to the gathers. The gathers are actually all of the traces that make up the seismic section. And when I see a one-dimensional and a two-dimensional model fit, I can say that's a good gas event. So in conclusion, what I'm doing is I'm pulling you up through the last 2 months of work and saying, I'm trying to wrap your arms around it. What's going on in the subsurface here? And now I have a better appreciation for the subsurface from 0 to 7,000 feet around here. And in this cube, what you see is the yellow is that salt face that we talked about. Outside the yellow is the disturbance volume, or the maximum area of disturbance or maximum area of uncertainty for a disturbance boundary. Where the gas is associated to the disturbance, what the Oxy 3 cavern response looks like, or at least its outline, and where its proximity is to the salt, how the caprock lays on top of the salt, some small faulting that seems to, buried faulting, it's all in the subsurface, that seems to bound the upper portion of the disturbance, which is highlighted in red, all below the sinkhole. The pins on this diagram represent old wellbores built between, again, the 20s through 2000. And they're on the outside of the salt, or to the left of the salt. And those were exploration guys looking for oil and gas along the west side of this dome. And for primarily about 90 years, they didn't find anything. So anything that's remaining in the subsurface is going to be right up against the salt dome. And that's what I think we found out here. And that gas up here is a very narrow window that's directly underneath the sinkhole. And so when we put this into motion, hopefully I'm going to end up with this slide. This will give you a kind of an appreciation in 15 minutes of 9 months, if I can find the button. I'm going to put this into motion so you can actually see it go. I can't see it, right? There we go. This is the beauty of 3D. We can look at things from the outside, we can look at things from the inside, put things in perspective versus the cavern, and try to understand the subsurface better. And I think from January to today, we've done that. And so now I take all of this interpretation, again, my best judgment of the data and interpretation of that, and port this to the next group of discipline, which is the Blue Ribbon Commission, to take my data, assess its value, assess its accuracy, assess its integrity, and then go forward and use this information to tie in with the shallow sinkhole and determine its longevity and its mitigation. So hopefully that was worth the 2 months of wait, and thank you so much for listening. I really do appreciate it. Dr. Pettit will now sing.
Yeah.
Okay, I'm not going to put you through me singing. So yeah, my name is Will Pettit. I've been here a few times now, met you guys. So I'm the English rock mechanics guide. I'm going to try and speak to you a bit more about what we understand is going on in the subsurface, This is a very busy slide, but I'm going to walk you through it. So what I've got here is I've got 3 columns. What we thought at the start of 2013, what we think now based on our knowledge gained in the last 9 months, and the future uncertainty and the knowledge to gain as we move forward. And what I'd really like to kind of put to you guys here is that you're really in the middle, we're really in the middle of an unprecedented event. And as we go through this, we are learning as we go. We're gaining knowledge, we're gaining understanding. We're recording data like Don just showed you. We're bringing all of that together and giving you our best interpretation and our best understanding of what it all means. So down the side here, I've got the DRZ shape and size, the sinkhole size, cavern fill, and salt dome stability. I'm going to go through these, and then I'm going to talk through some illustrations that summarize some of these points, just to kind of show you this in a bit more detail. So this DRZ, this is the disturbed rock zone. This is the connection, the physical connection that now exists between the cavern that runs up the side of the salt dome to the sinkhole. That connection provides a pathway for material and fluids to go down towards the cavern and for gas to come up towards the surface. Back in the start of this year, we did some numerical models, some rock mechanics models of what we thought was going on with that. And those models predicted a smooth banana shape for this this disturbed rock zone up towards the surface. And we said that there was probably 3-foot vertical displacement of material, broken rock, moving downwards about 600 feet away from the salt dome. Now what we understand from the 3D seismic is this is a more complicated picture. And I'll show you an illustration of this in a moment, why that's the case. We have a funnel-shaped upper disturbed rock zone to 1,200 feet. And then at depth, this disturbed rock zone goes through these kind of pinching. And that's all geologically controlled. And it's geology that we didn't have in our original models. But the mechanics is the same. The mechanics within the models is consistent with what we're seeing in the 3D seismic. What we are uncertain about still, and what we need to understand as we move forward, is what that structure of the disturbed rock zone actually means. What is the condition of the rock? We can't tell that so much from the 3D seismic, but we can try and understand that through the rock mechanics. Now it's essential to understand this because that disturbed rock zone is this pathway. So it provides the pathway for the gas coming to the surface, the connection into the subsurface gas zones. It is also essential for driving the sinkhole development, such as its size, the subsidence, and as I say, the gas that's coming up through it. The sinkhole size, our original estimate of the sinkhole size is a maximum of 1,500 feet circular diameter. And right now, the sinkhole is still within that. This maximum diameter was calculated using a 25-degree angle of repose. That's the stability of the banks of the sinkhole. And I'm going to illustrate that for you in a little bit as well. A 300-foot diameter disturbed rock zone, and this bulking up to 1.3, that's 30%. This is that, we illustrated it previously, where you dig a hole in your yard, and you always end up with some left over if you try and fill the hole back up again. Right? That's bulking. In this case, what we expected to begin with was that there would be about 30% bulking of the material in the disturbed rock zone sinkhole, helping to fill the cavern. We now think that that's not happening. And in fact, the bulking is about 1, because what we're doing is we're getting a lot of mixing going on as this material flows down. The shape of the sinkhole is actually an oval. We see it following the outline of the salt dome. The the edge of the salt dome. And these weak surface materials we've observed over the last 9 months is causing a very low angle of repose, so much lower than our 25 degrees. Now, of course, there's still uncertainty there. As we move forward, we need to understand better, we need to take more measurements to understand the final stable angle of repose, what this contribution of this disturbed rock zone is in terms of volume, and also whether there's any further salt dissolution going on that might increase the volume we have to fill in the ground. Moving on to the cavern fill, and again I'll talk about this a little bit more in a moment. The cavern is, back at the beginning of this year, we felt the cavern was about 85% filled with solid material. We now understand that's not the case. Instead, it's actually filled with this consolidating mud. So right in the top there, it's like a sloppy mud that's slowly consolidating under its weight, under gravity, with this more solid plug beneath. So again, the uncertainty moving forward is how this settlement occurs and how that material densifies and what that all plays into this bulking factor, this magic bulking factor. And where we see this being a key kind of effect is that the mixing of the materials that have flowed into the cavern have mixed up all the sands and the gravels and the clays, so to fill in all that pore space. So we think on average there's going to be 0% bulking, potentially. And then moving on to salt dome stability. Right at the beginning of this year, we didn't know what effect the failure of Oxy Cavern 3 had on the surrounding caverns in the salt dome. But through our modelling, we've predicted only minor effects on those caverns within the first few tens of feet away from the cavern walls. We've seen no indication of instability in Oxy 1, although that was a worry at one point. And Texas Brine has installed this shallow seismic array that's monitoring micro-earthquakes, and that showed activity in and around salt cap rock. So moving forward, we need to understand this a bit better. We need to understand whether our predictions have uncertainty in them due to some other effect that we haven't considered, like salt structure. We need to understand this behaviour of the cap rock and how that is kind of causing these micro-earthquakes and what effect that has on the sinkhole. What Texas Brine will be doing in the next month or so is installing a microseismic array deep within the salt. This is a 3,000-foot array that will be helping to examine the stability of the caverns. And I'll go through that a little bit more at the end of the presentation. So let's just leap back now to this disturbed rock zone. This is a section through the salt dome. This is the eastern side. This is the eastern. To the east of the sinkhole, the western side of the salt dome. This is the Oxy 3 cavern. This is approximately to scale. This was our geomechanical model that showed this banana-shaped disturbed rock zone leading up to the surface and the sinkhole. As I mentioned, this provides a flow of broken rock and sediments into the cavern and a flow of gas up towards the surface. We estimated that about 600 foot away from the salt dome would see about a 3-foot vertical displacement of the rock. It's moving downwards into the cavern. This is salt, this is sediments. What we've now discovered through the 3D seismic is that there are these strong limestone rock layers at various depths through the geological structure. What that's doing is it's causing the disturbed rock zone to pinch out. So it's got a lot more structure to this disturbed rock zone than we predicted. But approximately the same kind of size. It's about 600 foot at its maximum. What we don't understand from the 3D seismic yet is what this means in terms of the rock condition. And that's something that we'll be working on.